Sunum dosyamı şimdi paylaşacağım. Tam ekran görünüyor mu hocam?
Tam ekran görünmüyor.
Görünmüyor mu? Tekrar o zaman şu
F5'e bas.
bastım hocam.
Şimdi şey var, Windows tuşuna bas.
Tamam geldi ya.
Ha, geldi.
Tamam.
Tamam.
Good day, ladies and gentlemen. My name is Nurettin Arıkan, and the topic of my presentation is 3D printed piezoelectric polymers and applications in biomedical engineering. So here is the content of my presentation. I'm going to give a brief introduction and then mention what is piezoelectric effect and what are piezoelectric materials. Afterwards, I will pass on to fused deposition modeling, a well-known method of additive manufacturing. Then I will give several process parameters derived from literature, recent publications, so to say. Also, I will give a brief outlook about applications in biomedical engineering. And finally, conclusion and outlook, so to say, a future trend in 3D printing and 3D printing of engineering plastics, piezoelectric materials. Then finish my presentation. So, additive manufacturing, as we all know, additive manufacturing methods have recently attracted attention in terms of applicability, economy, and eliminating the limits that must be brought to designs if we consider subtractive manufacturing or other manufacturing methods. And it's possible to classify additive manufacturing methods in different groups. We can give examples such as SLA, stereolithography, or FDM, fused deposition modeling, as well as selective laser sintering, and so on. In total, there are 7 for some groups, 8 additive manufacturing methods, but fused deposition modeling, or as known as fused filament fabrication, is perhaps the most well-known method of additive manufacturing. Then filament development, and it's possible to feed different materials, different forms of materials in additive manufacturing. For example, for stereolithography, we use resins, and for some other methods such as selective laser sintering or binder jetting, material jetting, powders are used. And recently, fused granule fabrication, granule materials are deployed. But for FDM, filaments are used in different diameters. Afterwards, process development. It's important to identify and apply optimum parameters for each material. As you may know, in FDM, we feed mostly engineering thermoplastics such as polylactic acid, PLA, or polyethylene terephthalate glycol, PETG, and many more, ABS, ASA. But each material has its own properties such as nozzle temperature, build plate temperature, even printing speed, feeding speed, etc. And applications, materials here, functional layers, I would like to say, or the work pieces that are produced by adding these layers onto each other. Where could we use them as sensors, actuators, surfaces, or even functional models? I would like to give a brief information about piezoelectric effect. Piezo, the word piezing is derived from ancient Greek, and it means press or squeeze. Piezoelectric effect is actually an accumulation, the ability of certain materials to generate an electric charge in response to applied mechanical stress. In other words, we apply stress or we generate an impact onto a material, and it will create a signal, or here a very low voltage, an electric voltage, in order to process it afterwards. There are different studies on piezoelectric effect for centuries, I would say. Wilhelm Röntgen found out that rubber materials might generate static accumulations if they are treated or prepared with carbon black. But the most known study about piezoelectric effect is done by Curie brothers that was performed on quartz and Rochelle salt. And as you see here on the animation, after the mechanical stress on the material, it will generate an electric charge. What are piezoelectric materials? In nature, we can find ceramics or polymers as piezoelectric materials. Ceramics are known for their high piezoelectric constant, D33 here. Lead zirconate titanate, PZT, or barium titanate, sodium niobium, and barium zinc titanate. These are the most well-known ceramic materials, piezoceramic materials. And for polymers, polylactide lactic acid, PLLA, or PVDF, polyvinyl adenine fluoride. PVDF is the common used piezoelectric polymer because it has a piezoelectric constant not far from piezo ceramics, but PLA is weak, and researchers are currently trying to increase its piezoelectric constant as well as both mechanical and electrical properties by particle doping or piezoceramic doping. But to sum up, PVDF is the one we should consider. I would like to give some other details about fused deposition modeling and perhaps a brief history. As I mentioned before, FDM is the additive manufacturing process in which thermoplastic filaments are fed, mostly engineering thermoplastics, basic or high performance or high temperature. It depends on the application. The beginning of its history, actually, there had been some patents and applications for stereolithography or other additive manufacturing methods before this date. However, Stephen Scott Crump designed and produced a robotic arm, an articulated arm, to feed filaments and then generate the workpieces on the build plate. Those times it wasn't a heated build plate, just a simple build plate. And he applied his model and patented it in 1992. And especially in University of Bath in the United Kingdom in 2004, Dr. Adrian Bowyer and his assistants worked on an open source and huge volume printers in order to create even more detailed or high volume workpieces. And just after the patent protection of Stratasys or Scott Crump ended in 2009, they have been able to let it spread out and all over the world for more than 10 years. There have been many different and flamboyant printers, so to say, and in my humble opinion, we should thank them. They have made it possible to reach such technological devices, machines. And on the picture, you see an extrusion mechanism of an FDM printer, and on the right, Ender 3, Creality Ender 3 3D printer. I will show another picture in the next slide. Next slides, we have in our biomechanics laboratory 2 of these 3D printers and another model of Creality. And I would like to mention that although these basic FDM printers were much affordable in the beginning, after they were spread from China, the origin, they have also been advanced and progressed, and I will talk about them in the conclusion and outlook or future trends section. So here you see the working principle of FDM. In order to create a workpiece, we need initially an STL file. It's possible to use computer-aided design to generate any models. We can use SolidWorks, Shaper 3D, Siemens PowerSolid or NX, or even other computer-aided design programs. After we create our model, we let it sliced. The correct term is sliced, and we need to generate a G-code. There are both open code, open system slicers, as well as manufacturers specified, manufacturer dependent slicers. And after we get our G-code, we introduce it to the device, to the 3D printer, and the extrusion is performed by mechanical pressure and melting after feeding to the cold zone, cold end and hot end. The layers, as you see on the picture right, layers are generated onto the previous one, deposition, bonding, and solidification. So the principle in short is the deposition of new layers by moving nozzle and heat bed, layer by layer. And I just wanted to show several pictures, the filaments, or how we prepare them, and a closed cabin 3D printer on the right. And these are the ones we use in our biomechanics laboratory. And process parameters. I already mentioned the basic principle and the keywords, nozzle temperature, heat bed temperature, and so on. Nevertheless, for PVDF, we need to consider some other parameters, some other details. As you may know, some engineering thermoplastics tend to warp or shrink during printing. This is why they might require closed cabin systems, like in the industrial 3D printers. And I don't want to say it long and sum it up here. In the microstructure of PVDF, there are principally 4 phases, but sigma and delta and gamma phases are not commonly found. Here, alpha and beta are very important. Since PVDF is a semi-crystalline material, we need to facilitate the crystallization and get the beta phase, because it's both highly polar and it will exhibit ferroelectric and piezoelectric behavior after mechanical stretching or thermal treatments. I will let you know. The printing methods. In the literature, it has been reported that it's possible to print PVDF by SLA or FDM, but SLA is not common. I have found just two reports, two publications, but as for FDM, there are more than 20 publications in the recent years. And another important parameter is polling. Polling is not essential. I would like to highlight that. It's not essential. However, in order to increase the beta phase in the microstructure and make the material more piezoelectric, so to say, we might need some polling methods. What is it used for? It's the method to make it possible the orientation of dipoles along field direction by applying external electric field or thermal treatment, thermal forces. And I will give you, I will show some tables, and here the abbreviations. Nozzle temperature is THTA, heat bed temperature, printing speed, electric field, and so on. I will show you the tables in the next slides. And about the phases, on the left, for both images, on the left we see alpha phase, non-polar phase. It is found in pure PVDF or in the nature before polling or production mechanical stretching. I would like to say it in addition. Why FDM is used to produce PVDF for piezoelectric applications. Before 2015, 2016, it wasn't commonly known, and only some of publications were available to create piezoelectric PVDF, so to say, and it was either electrospinning or thin film methods, thin film coating applications. But as soon as it was shown that by mechanical stretching it's possible to increase the beta phase in the microstructure, researchers tended to utilize FDM since it's much more affordable and easier to process methods, I would like to add. And here is the table I would like to show. And as you might see, it's a very recent topic. Although my master's thesis is about thin film coatings and binders for lithium-ion batteries, we utilized PVDF just as a binder or as an agent. However, in the recent years, not for more than 5 years, it has attracted attention as a functional layer or functional surface material. And polling methods, as I already told you before, it's not essential. You see, no polling method was applied here. However, either during printing or after printing, it's possible to poll the PVDF layers to increase their piezoelectric constant, V33 again. And I will show you another image, how it is defined or measured. This one is from another publication, and this is an additional information I would say. It's possible to increase the piezoelectric behavior of PVDF either by polling as we already experienced, or by particle doping. And for particle doping, mostly the already piezoelectric materials, the piezo ceramics are preferred, barium titanate or zinc titanate. However, it's quite risky because the piezo ceramics or ceramic dopants particles are very abrasive, and they will probably wear out the nozzles after not excessive, but even short-term printing of these composite materials. This is why researchers are still working on different polling or stretching methods not to dope any particles into the PVDF matrix and only polymeric materials. How could we measure the 33 constant, the piezoelectric constant? This is one of the methods. There are commercial piezoelectric meters equipped with load cell or other sensors. You simply put your sample under the into the load cell, and after applying a predefined force, it will show how high the piezoelectric constant of the material or functional layer is. Here are some other process parameters. The earliest publication we have found so far is from 2017. As I mentioned before, before this year, I never run into a publication in which PVDF were mentioned as a piezoelectric material as a functional layer. It was solely a binder for lithium-ion batteries or membranes, etc. Applications in biomedical engineering. It's possible to deploy PVDF sensors or layers in many fields in biomedical engineering, not only as sensors, but also as actuators or for haptic tactile feedback, or some even functional buttons in biomedical devices and so on. Besides, it's also used as a functional coating on scaffolds. The scaffolds might be 3D printed, and afterwards PVDF might be coated by electrospinning or FDM again. And even for drug delivery, health monitoring, it has a very broad application area. And I just wanted to insert another image regarding the applications involved implantable devices. And here in the bottom left, you see a sensor, PVDF sensor, and the fingertip. It's possible to produce it in very small scales. This is another advantage. And maybe a very interesting application field is a retinal implant. Here in this image, in an implanted eyeball, it's possible to deploy a PVDF sensor or energy harvester, since it's piezoelectric, and it might generate accumulation not only by an impact or a mechanical force, but also from the vibrations or even moving in its environment, in its around. It will harvest some energy, perhaps in nano or micro scales, but it will initially be enough to generate at least weak or middle strong signals to process. This is also derived from a very recent publication. And I would like to conclude about PVDF. We can say within this frame, It's a non-toxic, lead-free piezoelectric material and FDA compliant. It might, since it's a very inert engineering thermoplastic, it might contact food or other substances, and it won't harm them as it's non-toxic. And PVDF has the other advantage. It's easier to process than ceramics. For more than 5 years, it has been discussed to shift to the lead-free piezoelectric ceramics. And here PVDF is much more advantageous since it's both lead-free and very easier to process than ceramics. It's also possible, as I mentioned before, to dope PVDF with piezoceramic particles or other particles, even pure sea salt, to increase its piezoelectric constant. However, I should highlight again, it will wear out the nozzles of your 3D printer, since piezoceramic particles are very abrasive, and even though they are homogeneously dispersed in the polymer matrix, it will still probably wear out any nozzles, and even hardened steel nozzles will suffer from their highly abrasive behavior from time to time. And finally, PVDF is available for numerous applications. There are commercial versions of this material, actually, some vibration sensors or some touch screens, but not very common as the other more affordable polymeric materials. And an outlook I would like to give in the end, what are the possible future directions? Firstly, multi-material 3D printing. As we already know, some thermoplastics, some engineering thermoplastics are able to, or they tend to stick to each other, like PLA and PETG, or ABS and some other TPU, thermopolyurethane. And especially for my dissertation, I would like to investigate if it would be possible to deposit some PVDF layers onto different thermoplastics, since it's already shown that some materials stick each other well by multi-material 3D printing FDM method. For this study, it might be required a multi-material 3D printer or an IDEX one, independent dual extruder. And there haven't been many studies or publications so far. This is why I already mentioned it as a future direction. A second one is that filaments with different fillers and particles. It was not very likely in the past to utilize wood-filled PLA fibers for standard nozzles or 0.4 millimeter diameter nozzles. However, in the recent year, it has been possible to produce even finer and better fillers, wood filaments, so to say, and they are able to be printed by even open system and very small diameter nozzle equipped 3D printers. And this should apply to the PVDF or PVDF composites too. Then, improving the ferroelectric properties of PVDF and even PLLA, it will be possible by either adding some dopants, fillers or particles, or different polling methods, as we already seen in the presentation, corona polling or thermal polling, or even electrode contact polling during or after the printing. And in order to overcome the limitations, non-poled piezo PVDF, it's also another field of study. especially a research group in Singapore. They have worked on this subject for several years, but they haven't published an exclusively detailed publication yet. And perhaps new piezoelectric materials other than PVDF and PLLA. There should be other engineering thermoplastics, polymers, or even ceramics in the nature or to be synthesized. To sum up, these should be the future directions for 3D printing and 3D printing of electroactive materials. Here are the references I made use of so far. And I would like to thank you for your attention and for your time. I might get any questions involving the subject.
Thank you. Thank you very much, Nurettin, for your interesting topics, your interesting study. I want to ask a question about your study. Do you think that which material properties can be changed during processes printing? Because that seems that only we heat the material and printing. Do you think that the material properties change? I mean, do you think that the piezoelectric parameters change from powder, not powder, particular phase to solid, because we made solid body. Could you explain?
Yes, it should actually change because our aim for the PVDF material, our aim is to increase beta phase in the microstructure. Since it's a semi-crystalline polymer, its advantages in this sense, because an amorphous or 100% crystalline material should be perhaps difficult to alter the properties, but here it's possible to alter the parameters and find an optimum temperature range under the Curie temperature range in order to increase the beta phase in the microstructure so that the PVDF will be the piezoelectric PVDF. Otherwise, if we let it keep the alpha phase even after the production of layers, it won't exhibit piezoelectric behavior, or we will probably have to pull it by means of thermal treatment or by high voltage charges, similar to the corona polling.
Okay, I understand according to your speech, and alpha beta phase in the material will change after the printing.
During printing.
Okay.
This is why researchers have shifted to FDM method, because just before it was found out that FDM made it possible to generate even more beta phases in the microstructure, researchers mostly utilized electrospinning method or thin film coatings, because under vacuum or by very high voltage charges, it was possible to increase the beta phases in the microstructure. This is why FDM will let a breakthrough begin, since it's much more affordable than electrospinning or thin film coatings, and it's a very simple method. The preparation, getting ready to print just in minutes.
Okay, last question. I would like to succeed I would like you to succeed your study. And after your study, which application will you made?
Very nice.
You made
Thank you for this question. I would like to return to the slides where the applications for biomedical engineering, it's a broad field, but I would say exclusively for sensor applications, perhaps for wearable technologies or even automotive interior applications. I would like to specialize. I would like to have my material specialized in perhaps the tactile feedback, the touch screen applications. It won't be as efficient as perhaps a touch screen of a smartphone, so to say. However, as I said, automotive interior application, or let's say an ENT motor control dashboard, it would be robust enough in the operation theater, operation room, or other fields to generate enough tactile feedback or generate enough signals to process and convert them into commands.
okay. I hope you will succeed making this material and this application. Again, thank you very much. And we will turn our friends, our listeners. Is there anybody to ask question, Nurettin? I think there is no question. Thank you very much again. And who is the next one?